Hi everyone, this is Sébastien Bardin and Manu Nguyen from Cerealist and Université Grenoble-Alpes, France. We are going to talk to you today about directed fuzzing and use after free bugs. This is joint work with our colleagues Richard Bonichon, Mathieu Lemaire and Roland Gros. So what's the talk about? Fuzzing has been proven to be great for finding vulnerabilities in the wild. Today we will focus on directed fuzzing, a slightly different setting where the goal is to reach a specific code target with application, for example, to patch-oriented testing. The problem we want to address is that current fuzzing techniques are very bad for some class of complex vulnerabilities. Here, use after free. Unfortunately, they are sensitive and can be critical. So we propose a directed fuzzing approach tailored to use after free bugs. And we'll show some application to patch-oriented testing. So first of all, what is a use after free? It's an error that occurs when some memory has been allocated, then freed, then it is still accessed after its lifetime through a dangling pointer. So there are some 3 points here. First, it is critical. It can lead to data corruption, information leak, denial of service attack, and so on. Second, there are more and more of them in the wild. Maybe a reason is that currently buffer overflow and so on are well protected and well mitigated, and many tools exist to try to remove them in advance, while use after free are still hard to mitigate and hard to find. Last point, it's quite a complex vulnerability actually. If you think of a standard buffer overflow, you just need at some point to go out of bounds. Where in that case, you have some kind of finite state automaton, like we see in the right corner, that you must fulfill before activating the issue. So as a teaser, here is a small example. You don't really need to know what this code snippet does exactly. The point is there is a use after free in it. If you go through the allocation, then the free, and then the use. Now, if you take IFL on this small code, actually IFL QEMU, to go on binary, within 6 hours, it cannot find it. If you take IFL Go, a directed fuzzer, which will work on source, and with an adequate trust target, again, within 6 hours, it will not find the use after free bug. With our technique called UFFuzz, within 20 minutes, we are indeed able to find this use after free bug. So first of all, a bit of context. So as most of you probably know, fuzzing is very popular for finding code level flaws. It has found many, many, many bugs. It is used by many security people and security teams, and many big companies are involved. Microsoft, Google, Apple, whatever you want, mostly. Actually, fuzzings come from quite a long time now. First, it means mostly random testing, which is called now black box fuzzing, and it consists in generating massive amount of input data, feed them to the program under test, and see if it's crash or not. Okay, it was very simple, but it turns out to be very effective. But along the years, it had made huge progress, so now there are 3 shades of fuzzing. So there is still this black box approach to fuzzing. There is also something called white box fuzzing, which use lots of advanced program analysis techniques to find bugs, but which has problem with scalability. And there is gray box fuzzing, which try to take the best of both sides, scalability from black box approach and cleverness from white box approach. And actually, IFL was probably the first gray box fuzzer. It was a very pioneering and inspiring work, and it has been very, very successful. And now this is a very active research area with more and more new ideas to move the sweet spot and add more and more intelligence in the tool without any scalability penalty. So I give you just a little test of what fuzzing is. So basically you have a set of input. You need a way, some heuristic to choose a good input to select which are the best one. So for example, those input which activate new part of the code, for example. Then you will create lots of new input from them, from mutation, so input which looks pretty similar to the initial good input, but a bit different. And then you will simply run them all against the code under test, observe their behavior, compute their score, take the best again, and then mutate them, and so on in some kind of evolutionary process. So here the big difference between black box fuzzing and gray box fuzzing is that in black box you cannot observe a lot, especially mostly only the output. In gray box you can observe typically coverage information, stuff like that. Obviously, fuzzing is not a silver bullet, so it can have a hard time covering very complex condition or going very deep inside the code. Okay, it has a hard time with complex bugs like use after free. We will discuss that after. And it may also have a hard time to do some target-oriented testing, where the goal is to cover some specific part of the code. So regarding this last point, recently a new flavor of fuzzing has emerged, directed fuzzing, that precisely aims at tackling this problem. So you take an additional input, which is a target, either a trace, a code trace or code location. And what you want is to find an input which will cover this trace. So either cover the trace or reach the location. So it has interesting application in security, such as bug reproduction. So typically you have some partial information report on a bug, but you don't have the input, the triggering input. So with directed fuzzing, you can try to find the triggering input for this bug report. Patch-oriented testing, where you will try to direct your testing towards some specific part of the code, typically a patch. And for example, confirmation of static analysis report to see if there are false positive, false alarm, or real problems. The very, very first directed gray box fuzzer was AFLGO in 2017. So this line of research is kind of new. So from a more technical point of view, actually coverage-guided gray box fuzzing, so standard gray box fuzzing, and directed gray box fuzzing are not that different. So this is a high-level view of coverage-guiding gray box fuzzing. So first you have some instrumentation step where you will add to the code all the information you need to record typically coverage information. Then you have the fuzzing loop by itself with seed selection, mutation. Also you can give some power schedule which is time budget to seeds according to their score, with a good seed having better score and so on. Then you need also a way, which is called here triage, to distinguish between bugs and non-bugs. So for buffer overflow, it's pretty simple actually. When it crashes, then you have a bug. You can miss a few buffer overflow, but most of the time it will be okay. For something like use after free, it will be much more complicated, so we'll see. So now, if we look at directed gray box fuzzing, it's mostly the same. So you have an additional input, which is the target, and one additional component, which is the seed distance, meaning the distance between an input, the execution of an input, and the target you want to reach. Once you have that, then basically it follows the same architecture, except that typically some part of the architecture will take the distance into account. For example, the power schedule. So now, coming back to use after free. As we saw before, there are more and more of them. Yet, actually, further do not find a lot of them. We have statistics from OSS Fuzz on the right part. Actually, there are deep reasons for that. There are two main difficulties for ending use after free bugs with fuzzer. The first one is that there are very strong temporal and spatial constraints for this kind of bugs. They are very, very complicated because you have this temporal constraint. You need to find an event, a sequence of events. So the allocation, the deallocation, and the use in this specific order. And also some spatial constraint because all these events must relate to the same memory cell. And here already fuzzing has a really hard time compared to buffer overflow, where typically you just need to reach one point in the code with big enough arguments. The second point, which is hard for fuzzing, is that usually for use after free, you don't have any crash. So it's kind of a silent bug. So what people will do if they want to find use after free with fuzzing is to equip fuzzer with a sanitizer like Valgrind, and so to run it to run sanitized execution. But there is a big runtime overhead with that, and this is a problem actually, because fuzzing is good because it is able to create a very huge amount of input. So if you have runtime overhead, you will run much less input and you will be less effective. So this is a big problem too. So, and actually it happens that both fuzzing and directed fuzzing have a very hard time in practice on use after free. So recall our tiny motivating example. So now that I have set up the stage, Mandung will explain our technique for use after free directed fuzzing.
Thanks, Sebastian. I will present UEFA's a directed fuzzer for use after free bugs and then draw some conclusion. Before discussing our techniques, so we first revise the workflow of directed fuzzer and show the limitation in finding use after free. Existing directed fuzzer are distance guided, so however, the instrumentation phase at source level is costly, around several hours for complex programs, and it cannot differentiate the differences between two inputs covering the same set of basic blocks but in different order. Existing wave-up fuzzing treats edges equally. However, given a set of predefined targets, the likelihood of edge destination being reachable to targets are different. Consequently, in some cases, they might waste effort exploring non-vulnerable code or invisible paths leading to specified target. Also, previous work don't take into account the orderings of cover basic block when selecting inputs for mutation. They might skip input that already cover in sequence several target basic block. Next, as UAF bugs fail silently, we need to choose on input produced by the fuzzer to find the proof of concept input. Such a large amount of unreachable input wastes a lot of time in the sanitizer-based choice process. To address the limitation discussed above, so we propose UAFAS, a directed fuzzer dedicated to use after free bugs by carefully tuning the key component of directed fuzzing to meet specific characteristics of this type bug. Overall, UEFAS has a similar workflow as directed fuzzer, and we add our improvement highlighted in orange along the whole fuzzing process. First, the static pre-computation of UEFA is fast at binary level. Second, we introduce new input metric to guide the fuzzer toward target at runtime. Finally, we choose only potential inputs covering all targets in the expected choice and pre-filter for free inputs that are less likely to trigger the bug. Overall, we select inputs for mutation based on similarities and orderings of input choice compared to the expected choice. We assess the likelihood of an input based on three metrics dedicated to UAF at different levels of granularities: function calls, edges, and basic block. So the more fine-grained the metric is, the more precise the analysis is in terms of identifying interesting inputs that are likely cover the expected trait. So in next slide, we will detail our input metric. And we focus on bug reproduction and pass testing application. So it's more likely we have a complete stack trace of on-memory related UF events. So in this case, unlike existing zero-related approach, we need to take into account the relationship among targets to improve effectiveness. So to facilitate our further analysis, we must own stack trace as shown in the figure on the left-hand side to recreate a dynamic calling tree. Then perform a pre-order traversal of this tree to generate a bug trace at our target. So we make sure that the children are ordered according to the orderings of the EOF event after the flattening process. Previous seed distance do not account for any order among the target location, why it's essential for EOF. So we address the issue by actually modifying the distance between functions in the cone graph to favor paths that sequentially go through the three EOF events, allow free and use of the bug tree. This is done by decreasing the width of the edge in the cone graph that are likely to be between the events using lightweight static analysis. So our distance-based technique therefore consider both calling relation in general. For example, in some cases where the calling can appear several times at different locations in the caller, and the calling relation covering EOF event in sequence. As existing work treat exists equally in terms of reaching sequence targets, we propose a lightweight cut-edge coverage metric by measuring progress at level, but on the critical disease node only. First, we statically identify cut-edge whose destinations are more likely to reach the next target in the bug tree. As shown in the figure, it's lightweight because we only perform static intra-procedure analysis of control flow graph. At runtime, UFRs favor inputs exercising more cut-edge via score depending on the number of covered cut-edge and the hit count. The sequence-aware target similar metric concretely assess how many targets a seed execution tree cover at runtime, and also take orderings of the targets into account. We combine both prefix and back option, as prefix option is more precise because it counts value until the first diversion in the bug tree. And the back option also provides more information about the whole tree. Then we use this metric for seed selection by actually selecting more frequently input that are most similar to the target bug tree. So overall, UFRs prioritize or assign more energy to input in the following cases. First, inputs that are closer to the bug tree by our distance metric. Second, inputs that are more similar to the expected tree by our target similarity metric. Finally, inputs that make better decisions at critical code junction by our cut-edge coverage metric. In the triage process, UFRs triage only potential input which cover in sequence on target location in the bug tree. So we obtain this kind of information for free via our target similarity metric. For implementation, we build our two UFRs on top of the popular Fuzzer FL in QEMU mode. We use IDA-Pro to get the control flow graph of the tested binaries, and we also aim to support more open source binary disassembler like Radar. And then we develop plugin of the binary analysis framework being set for static computation. Finally, we use the profiling tool like Vanguard in the triage process. For evaluation, we evaluate our approach in two applications. So for bug reproduction, we compare our tool with the state-of-the-art guided and grid fuzzer on 13 UAF bugs of real programs. As AlphaGo is a swap-based fuzzer and Hawkeye is not available. So we implemented their core techniques on our framework. Also, we use time to exposure, number of bug file overhead, and number of charging input as comparison metric. And you can see in the figures, UEFAs outperform state-of-the-art further in terms of bug reproduction with a high confidence level. For example, UEFA found bug 2 times faster and 34% more bugs than the second best fuzzer. UEFA also enjoy both a lightweight implementation time, for example, 15 times faster than the swap-based AlphaGo, and a minimal runtime overhead compared to the AlphaQmu. UEFA reduce a large portion of choosing input, around 90%, and spend only second in post-processing phase. So another practical application of predictive fuzzing is path testing. So the goal is to find incomplete patch or regression bugs. Also, by exploring around the previously vulnerable code, we could find new bugs. So how do we do? First, we identify recently discovered UAF bugs of open source programs. As the code has evolved, in some cases, we need to manually extract code instructions in the bug trace and use them as target to guide UEFAs. So actually, UEFAs found 13 new bugs, and 4 of them are incomplete UEF bug fix in critical programs and got 7 CVEs. This table details our finding. For example, we found an incomplete fix of GNU pass by using the bug tray of existing double free. So to summarize what we went over in this talk, we propose a directed fuzzing framework to detect you after 3 bugs at binary level. And we saw its effectiveness and efficiency in bug reproduction and path testing application. So 4 key takeaway points of our talk. So first, directed fuzzing is practical and should be integrated into the software development process. Second, we should develop vulnerabilities-oriented fuzzer to actually effectively detect complex bugs. And third, patch-oriented fuzzing is bigger than bug testing. And finally, we should find and fix variants of bug class. Thank you for your attention, and we check out our paper and our tool. So we're happy to take any question.
Hi everyone. In the internet connection. So if you have any question, we'll be happy to answer it. Okay. So So yes, there is a GitHub repo. Actually, I think it's the last slide. So there is a GitHub repo on the slide. You will have the address. Okay, so a lot of questions coming. Um, so Kenta, regarding your talk. So we have a GitHub. Kenta, regarding your talk. Indeed, the main idea is behind UFOs is to realize that usual directed fuzzer just don't really take into account the specificities of the bug they are looking for. It's good for memory overflow, but clearly this is a problem for use after free. And so we try to take that into account. And here, one of the very important point was about sequenceness ordering. So that's one point. But there are also other things, but it's the idea of all these metrics that Mandung just described. It's all about um, putting intelligence, putting knowledge of the vulnerability, of the kind of vulnerability inside the directed fuzzing process. And it's why it works better. Question, so what kind of program did we test again? This is probably more question for Mandung, but at the end of the slides, you will have so basically a table with a different vulnerability we found and so on. So basically, we have two kind of experiments. On the one experiment, we compare with other directed fuzzer, but which are not tailored to use after free. So we take their benchmark. So I don't really remember. We take use after free bugs on some programs, take patch version and see if we can find bugs in this patch version. So in this case, we have programs like a GNU patch, Perl 5, new PDF, some stuff like that. So we have also a technical report on the web. There is also some address in the slide, and there are much more detail on that. Okay, so there is a white paper. Actually, there is even an academic paper which has been accepted to read. This is an academic conference. So the paper will appear, I guess, in September, and I think there will be anyway a technical paper before that on my webpage and on the webpage of Mandung really soon. We have a camera ready version, so and we have all the details about the programs, experiments, data, and so on. Oh, perfect. So Harrison, I will let Mandung answer for this question because actually I'm not sure. He's the main programmer and designer of the tool. Actually, I would say regarding Valgrind, unless Mandung saw the thing, but I would say that it can. The thing is, from Valgrind, the thing we take is really the what we really need is about the kind of bug trace, the kind of format. So that's not a very big problem. Any other question? Okay. So I let you, let's say 10 seconds for last question. Otherwise we stop. Okay. Thank you guys. That was really, really interesting. Hope you enjoy it and see you next time. Bye.